Hello everybody and welcome to another video of lesson on the Fourier transform. In this case we are going to do exercise number 6 of the handout. And again, as we have done in previous exercises, we are to find the output to a certain input of an LTI system, linear time invariant system, which has a frequency response as the one shown here. In this case, the input, as it was in exercises 5 and 4 before, is not a periodical signal, but it is a certain signal x of t given by this expression. And we have to find, in this case, not the output signal x, but the energy of the signal at the output, and this energy will be a function of a variable or an unknown, which is W, which is the bandwidth of the filter, or the bandwidth of the frequency response. By the way, this is a filter because it filters the input into the output, and the type of filter in this case, it's a low pass filter because, as you can see from its plot, the plot of its magnitude, it only allows the low frequencies, the frequencies that are between 0 and a maximum of W, capital W, to pass through the filter. Okay, so we could do one thing, which is calculate x, then calculate the Fourier transform, then calculate the Fourier transform at the output as the input times the frequency response, and then finally calculate the energy of the signal using the expression of the energy of the signal in frequency. But we will take another tour here, and we will introduce a very important relationship in linear systems, which is the following. If you have a certain signal at the input with spectral energy density xx, and you know h of omega, the frequency response of the system, and you wonder what will be the frequency response of the spectral density, energy density of the output. Well, this is a well-known relationship that you should commit to memory, which is the energy spectral density of the output is the spectral energy spectral density of the input times the modulus of the frequency response square. So that's a very, very important relationship. So in our case, we know x, so we know what's the spectral density energy of the input, which, as you know, is the modulus of the frequency, the Fourier transform of the input square. So in our case, the spectral density of the output will be the modulus of the Fourier transform of the input to a square times the frequency response square. So once we know this, obviously the energy at the output, we know it's always is 1 divided by 2 pi, the integral of the spectral density energy at the output times the W. So again, this with the formula that we have just calculated here, we will calculate like 1 divided by 2 pi modulus of the input signal square times h omega square d omega. Okay, so this is how we will calculate what they are asking for. So we know this because we know h omega, and so we need to calculate what is the square modulus of the Fourier transform of the input x, and we know xt. Okay, so let's calculate the Fourier transform capital X omega of the input xt. And in order to do that, we are going to use one of the Fourier transforms of the table, which is the following. The exponential of minus one constant b times the absolute value of t, the Fourier transform of that is 2b divided by b squared plus omega squared. Why are we using that? Because really it resembles quite closely to our function x of t, but unfortunately it resembles it but in frequency. So we would like to have this expression the other way around. So what do we do? Well, we use the duality property, and we take this 2b and we put that in the left side. So we put this, and obviously the variable is no longer w, the frequency, but t. And this, using the duality, is the exponential and of minus omega. So you have to change the variable t to omega and also multiply this by 2 pi. Because the absolute value of minus omega is omega, and this will be 2 pi e to minus b absolute value of omega. Okay, and this is really what we need to calculate the Fourier transform of this, because if we make b equal to 1 in this expression, we will have 1 divided by 1 plus t squared, and this has a Fourier transform which is 2 pi e to minus absolute value of minus omega, which is almost what we have here. The only difference is that what we have is t minus 1, and in this case we have only t, but we know that we can solve that with the property of translation in time. So meaning that if in our case what we have is t translated 1 unit in time, the Fourier transform is just taking the Fourier transform without any time translation, and we just multiply that by an exponential which has a coefficient the same as the translation in time. So finally what we have what we want, which is the Fourier transform of the input. But remember that what we are looking for is the modulus of the Fourier transform square. So what is the modulus of this? Well, very easy. The modulus is this part here, because this is obviously a phase, an exponential with a phase minus omega. So in this case will be just 2 pi times e to minus absolute value of omega squared. Okay, and this is for well, there is something else that I am forgetting. No, I think it's correct. So this will be 4 pi squared e to minus 2 absolute value of omega. Okay. I think I didn't forget anything. Okay, yeah, so well, finally what we do is we calculate then the energies of y using this expression. It will be 1 divided by 2 pi integral of the square of omega, which is 4 pi squared e to minus 2 absolute value of omega, times modulus of h omega squared d omega, and this in principle is from minus infinite to plus infinite, but we know that h omega is only 1 for the interval between minus capital W plus capital W, which we express just changing the integration limits. And then this will be 4 pi squared divided by 2 pi, and then the integral will only be between minus W and plus W of e to minus 2 absolute value of omega d omega. And obviously this is a very easy integral because this is a pair integral. We can duplicate and say this is two times the integral for p squared divided by 2 pi integral between 0 and omega of a minus 2 w diferencial de omega. I'm changing here into Spanish, okay. Well, so we simplify this a little bit, and well, if you calculate this, very easy, at the end you should get p divided by 2, 1 minus e2 minus 2 capital 2 omega, okay. This is the energy of the output signal. That's it. So recapping a bit, the important topic that we have learned here is that we can calculate the energy spectral density of the output as the energy spectral density of the input times the square of the modulus of the frequency response. So that's the first important topic that allows us to calculate the energy at the output. And then the other important topic that we have learned is by using these pair of transforms, we use duality, and we get the transform that we need to calculate the Fourier transform of our signal. So I hope this exercise is clear. Otherwise, let me know. Thanks for your attention, and see you on the next video. Bye-bye.